I often explain a Bose-Einstein condensate with the analogy of light. So, everybody knows by now that there is a big difference between light coming from a light bulb and a laser beam. And you can describe the difference that a light bulb emits light in all directions. The photons are in different modes. It's incoherent light. Whereas light out of a laser beam is monochromatic, and you can say all the photons march in lockstep in the laser. They propagate in the same way. And now the same distinction applies to a Bose-Einstein condensate now in the material world. In a thermal gas, atoms move randomly in all directions. They are incoherent. Whereas when you have a Bose-Einstein condensate, all the atoms march in lockstep. They are in one mode, they're in one quantum state. So if you want, which is not always easy, to explain a scientific discovery in one sentence, I would say it in the following way. The Bose-Einstein condensate is for atoms, what the laser is for light. Okay. Or Bose-Einstein condensation means that we have matter, atomic matter, with the properties of laser light. 1920 or so, these were in the early days of quantum mechanics, when people had not developed yet the understanding of quantum mechanics a la Heisenberg and Schrödinger, but they had a Bohr model, they had Planck's explanation for the black body spectrum, and they had the idea of photons by Einstein. And what happened is that the Planck spectrum for black body radiation was well known from, what was it, close at the turn of the century, I think, when did Planck discover the black body spectrum? 1898 or something, so it was really at the turn of the century. But then Bose gave a re-derivation. He derived the Planck spectrum in a new way. And it was done in a way where he looked at photons and calculated the number of possible quantum states in a statistical way, and out came the Planck spectrum. And when he submitted this paper he asked Einstein to help him to publish it in Zeitschrift für Physik, Einstein immediately realized that this treatment of Bose, which was for light, for photons which have no rest mass, could be immediately applied to atoms and molecules. And so pretty much within no time, Einstein generalized Bose's treatment to atoms. And then for atoms, the treatment predicted Bose-Einstein condensation. For photons, you don't have Bose-Einstein condensation. But if you add a rest mass, the mass of an atom, and you have conservation of mass, then the black body spectrum turns into the Bose-Einstein distribution. And at sufficiently low temperature, the Bose-Einstein distribution has this phase transition into a Bose-Einstein condensate. I know when people feel uneasy about quantum mechanics, it is about what people call the quantum measurement process, but this is not related to the predictions of quantum mechanics and the usefulness of quantum mechanics. It's more an uneasiness about the philosophical interpretation of quantum mechanics. So I often feel when people say when people say there's a quantum measurement problem, I sometimes say, hey, wait a moment, this is not a problem of science, it's a problem of philosophy.
Okay.
Because for everything we do with quantum mechanics, we have a quantum mechanical system and we have a measurement apparatus, and we absolutely understand how to make those connections.
Okay.
Maybe I should say now, if you press me hard, I see a little problem when you ask me what is the wave function of the universe. Because if you talk about the wave function of the universe, there is nobody outside the universe to observe the wave function. Mm-hmm. And quantum measurements always need a quantum system and an outside observer. So if you press me hard, I would say, okay, maybe there is a scientific problem to understand also conceptually what is the wave function of the universe. But if you think about, every wave function of a microscopic system and we do measurements on them, we know exactly what we are doing. But people who debate, the different interpretations of quantum mechanics, for instance, the Bohr interpretation or the Copenhagen interpretation or the many worlds interpretation, I mean, if all these different interpretations do not make different predictions, this is a question which is untestable. And a scientific hypothesis should formulate alternatives, and we can do experiments to distinguish between alternative theories. But if we have alternative interpretations of quantum mechanics and there is no prediction which allows us to distinguish about it, then for me it's not a question of science. It's a question of personal preference, or you can say a question of philosophy. And if people postulate a different form of quantum mechanics and they make predictions, then it's testable. Okay. There is one school of thought which is related to Roger Penrose. He suggested that some collapse of the wave function is caused by gravity. And now some people have added nonlinear terms, new terms to the Schrödinger equation, and this is now making new predictions which can be tested. Okay. Unfortunately, some of those theories make predictions which would deviate from the predictions of quantum mechanics only when you have superposition states of macroscopic objects. And that this is something which is extremely hard to produce. However, there are few experimentalists who try to put a quantum object, macroscopic quantum object, into a superposition state to maybe verify or disprove some of those hypotheses that there is a gravitational form of decoherence involved in quantum mechanics. So what I just said is this is an example where people have come up with some predictions which are different from the normal predictions of quantum mechanics, and maybe with a big effort in the future, they can become testable. Yeah. And we now understand theoretically, for instance, these beautiful experiments, if you have an ion in an ion trap and it does quantum jumps between, a ground state and a metastable level, and you can really see how the wave function collapses in one state, then in the other one and such. So you really see quantum jumps. But even before those quantum jumps were discovered experimentally, some people thought this would be nonsense. This would not be how nature behaves. So I would say the step, also we use still the same quantum mechanical equations, but the way how to know what is the wave function applied to single microscopic objects. This is modern physics. This enables the quantum computer, and this was not on the mind of the people who developed quantum physics. Well, quantum mechanics has really been tested in a wide range of regimes. So it's not that our understanding of the world will be invalidated. It's a little bit like, Einstein's theory of relativity. It doesn't mean we cannot use Newton's equations. For 99% in your life, we can use Newton's equations and the engineers use them. It's just that Einstein taught us that when we go to extreme speeds, close to the speed of light, there are fundamental corrections. And maybe similar, just referring to the possibility that, when we combine quantum mechanics with gravity, that we find some gravitational form of decoherence. This could be important at the fundamental level, but it will only correct our understanding for systems in very extreme parameter ranges. Okay. As I said, maybe macroscopic superposition states, which are very, very difficult to create because they have very, very fast decoherence times. So, but yeah, that would, to discover that there is a new type of quantum mechanics needed to describe mesoscopic objects, this would be amazing. It would be an amazing discovery. Okay. Yeah, so Bose-Einstein condensation was realized by, taking a gas of atoms, down to very, very low temperature. And when I entered the field, some pioneers in atomic physics had just developed laser cooling. I joined the field in 1990, and people had developed amazing methods of laser cooling, and in 1997 they got the Nobel Prize for it. So laser cooling, which allowed to get into the microkelvin temperature regime, was the first step to reach Bose-Einstein condensation. We had to add a second cooling method to go from microkelvin to nanokelvin. But laser cooling was an absolutely important first step. Now, laser cooling itself is amazing, and it's actually, yes, it would defy the common understanding that lasers heat. But I always explain it like that. Lasers are a form of energy. And you have a black t-shirt on. If I would shine a powerful laser on your t-shirt, you would feel the heat because the photons disappear. The photon energy is converted into vibrations of the molecules in your t-shirt, and you would feel the heat. But in laser cooling, we use atoms which cannot absorb the photon. They can only absorb the photon for very, very short time, and then they have to re-emit the photon. So therefore, atoms are never absorbing the energy of the photon. They are not converting light into heat. So atoms, at least in some idealized form, do not absorb light. They scatter light, photon in and photon out. And then you would say, okay, if the photon is not absorbed, there is no cooling and no heating. But now we are looking at a smaller difference. The photon which is scattered can have a slightly higher or slightly lower frequency than the incident photon. The color of the light can change. And the simplest reason why this could happen is the Doppler effect. So if you arrange for a situation where the atoms scatter light, and the scattered light, the scattered photon, has a little bit higher energy than the incident photon, then every time an atom scatters a photon, it radiates a little bit away of its energy. Okay. And then it gets colder and colder. Okay. And so this is what is behind all laser cooling schemes. You create a situation where the scattered light is slightly more energetic than the incoming light. And this enables atoms to literally radiate away their energy through the scattering of photons. We used laser cooling to the extent possible. We prepared laser-cooled samples of atoms, but those laser-cooled samples were still far away from Bose-Einstein condensation. And we also reached the limits of laser cooling, because if you try to apply laser cooling to colder and denser samples, the lasers actually start to heat. There are processes that, the discreteness of the photon means that in normal laser cooling, there is a limiting temperature called the recoil temperature. You can only cool to that temperature, but you cannot get colder. When you get very dense atoms, and Bose-Einstein condensation is about cold and dense atoms, these dense atoms will absorb the light. There will be multiple scattering of light. The light is not just scattered once, it's scattered many, many times. And this causes limitations. So to make a long story short, laser cooling had reached a limit before Bose-Einstein condensation happened. So it was essential to devise a second method of cooling which could take the laser-cooled atoms to even lower temperatures. And this method was evaporative cooling. So the critical step to realize Bose-Einstein condensation is to find to combine both in a conceptual and a technical way two different cooling schemes: laser cooling and evaporative cooling. Yeah, we have now for many years started to assemble quantum systems out of cold atoms and understand their behavior. And if we have new building blocks with long-range forces, there are other phenomena and other materials we can study.